Hello everyone, this video is going to be on CapM, the capital asset pricing model in Python. This video is kind of a sequel to my video on Markowitz portfolio optimization in Python. So just to remind you guys, in that video what we did is we showed you how to find optimal portfolios by either maximizing returns subject to a given level of risk we're willing to take, or equivalently minimizing risk subject to a minimum return we want. And then we saw how you get like optimal portfolios and they lie on this efficient frontier. So please watch that video for more information. So this video was about CapM, which greatly simplifies Markowitz portfolio optimization, makes it a lot more practical, and it gives things like the notion of systematic versus specific risk. So I'm going to explain CapM big picture, and then I'll show you how to do CapM regression in Python with stats models, and I'll show you in particular like some cool tricks to do a ton of multi-dimensional regressions at once. If you guys used R in the past, this might give you nostalgia because we're going to use like the formula API. So let's get the show on the road. Of course, please like and subscribe. It means a lot and it helps YouTube give me some relevance. So let's get started. So the big picture is with CapM is basically you relate the return of an asset to the return of the market as a whole. So the basic CapM is basically expected return for an asset equals the risk-free rate plus some beta times expected market return minus risk-free rate. So it's probably better if we would have put the risk-free rate on this side. So we get expected return for an asset minus risk-free rate. This is also known as the expected excess return for the asset equals beta times the expected excess market return. So what this means is basically you expect the return of an asset to be related to the return of the market, and beta basically tells you how much it's related. So like a beta is 1, the market goes up by 1%, your asset goes up by 1%. A beta is 10, the market goes up by 1%, your asset goes up by 10%. That sort of thing. Okay. So, yeah, but of course, you see it's already kind of messed up. Number one, of course, the assets shouldn't just be related 100% to the market. There is definitely things that are unrelated to the market. But the most simplest flaw here is some assets are better than others. Some are just better. So that's where you have this idea of Jensen's alpha. So basically, if you subtract this right-hand side from the left-hand side, you get like the basically how much better the expected return for the asset is minus what you expect under CapM. This gives you something called alpha. So alpha is the actual return minus the risk-free rate plus beta times the excess market return. So alpha is basically how good you are, how good the asset is. A positive alpha means it beats the market. A negative alpha means it's worse than the market. This is where the whole like lingo in finance of like seeking alpha or a strategy with alpha comes from. It comes from this. But we're going to actually talk about CapM regression, which is a bit more mathematical. So basically, we could formulate this whole thing is, let's say we have like n assets, any asset in the world. The CapM has the risk-free rate of the return of asset I minus the risk-free rate equals alpha I plus beta I times return on the market minus risk-free rate plus epsilon I. So this is a random quantity. Return on asset I is random. Return of the market is random. But we're assuming that the return of asset I is only related to the market, return on the market through this beta I, and an epsilon I, which is specific to asset I. So each asset has their own epsilon I, and CapM assumes that the epsilon I are independent, uncorrelated. So basically, for if you have the same one for asset J, the epsilon J is uncorrelated to epsilon I. So if you look at the correlation of the returns, you see that they're only related through the market itself, which is kind of a bit weird for things like, let's say, AMD and NVIDIA. It seems like although year to date, AMD is actually down and NVIDIA is up 200%, but hour to hour, the correlation is pretty strong. It seems way more than just the market, related to the market. But for something like maybe, let's say, Roku and AMD, then I guess that makes sense that they're only correlated through their correlation to the market. And this epsilon I is basically something you can't, is error specific to the asset. And alpha I, as we spoke about previously, is basically how much better the asset is than the market. And beta I, of course, is how it moves with the market. So if the higher the beta, the more it moves, the lower, the less it moves with the market, that sort of thing. So this is what we're going to actually try to do in Python. We're going to literally try to calculate the alphas and betas for every single stock in the S&P 500, each of the individual stock. We're going to use the market, the benchmark, as the S&P 500 index itself. And you're going to see kind of what stocks are the best and what are the worst. So this code is available in Medium. So you can just go to the Medium link and you'll have the code. But I want to kind of cheat and show you the winners. So the top, I plotted the top 20 stocks and the bottom 20 stocks by alpha. SMCI, or my boys SMCI that cost me so much money, are number one. NVIDIA is number two. That makes so much sense. This is over the last 5 years. Tesla, that shows you, of course, like regressions, linear regressions are not that great. Tesla and NVIDIA make perfect sense, of course. But SMCI doesn't really make much sense, especially like because of the crash. Interesting that Broadcom and Dell and those things are on the top. Some of the bottom ones, Boeing, good old Boeing, unfortunately is bad. And then like I plotted the betas also, and it's nice to see Tesla near the top because Tesla moves pretty much a lot with the market. So that's good to see. And I'll show you how to do this in Python. But just before we get to that, I want to talk about two quick things. Number one is there's a thing called the security market line. So this is just the original CapM formula, basically. Is saying like, okay, so the CapM formula above is basically saying you have expected return for the asset is risk-free rate plus beta times expected market return minus risk-free rate. So this is like the fair value of return. So if you plot this for given beta, you'll get a line. So the line will look like this. For each beta is a point on the line, you get this stuff. So if you're above here, it means your expected return is higher per beta level than what you expect under CapM. So these will be like undervalued stocks and below will be overvalued stocks. So I'll also show you in Python how to get this line. But just one last thing I promise before we get to the Python part, which you're all waiting for, is the idea of systemic versus specific risk, which is a big thing about CapM. So systematic, I always say systemic. Systematic risk is market-related risk. This is risk related to the market. So like no matter what you do, like let's say your asset goes up, like let's say you're diversified as hell, but unfortunately all your assets are related to the market. So if the market tanks, your assets will tank no matter the diversification. But there's specific risk. These are assets specific to these are risks unique to individual assets. So a good example of specific risk is like there was a day where SMCI tanked so much, and AMD went down a lot, right? But the market I think was green overall. So like the systemic risk, the one specific to SMCI and AMD were down. That's after AMD's earnings and SMCI's whole accounting resignation. Those are the systemic specific components. Those. But the market risk wasn't a factor. But the thing is if you, let's say, have a portfolio of like n assets and you give them equal weight, roughly speaking, this is wrong, but it's close enough in approximation. Your return for your portfolio, like this RP thing, is like the average of the individual asset returns. And if you plug in the formula, I'm ignoring risk-free rate here, for CapM, you'll see that it's like 1 over n plus the sum alpha I plus beta I, return of the market plus epsilon I. And if you take the variance of this, I'll spare you the math, you'll have a systematic risk component, and a specific risk component. So what's cool about the specific risk component is because with variance of a constant is you take the square of that. So this will be 1 over n squared times the variance of the sum. So this will be of order 1 over n. So the specific risk will go to 0. And I should have made that more clear in this math. So what's cool is diversification saves you from specific risk. So like if your whole portfolio was an SMCI, you would have, like, I mean, mine a lot was an SMCI, but you would lose a ton. But if you're super diversified in the limit, you have no specific risk. Okay, so now let's get to Python. So one last tiny thing before we get to the Python. I should have mentioned that in this region of undervalued stocks, it corresponds to alpha greater than 0, and the region of overvalued stocks below here corresponds to alpha less than 0. So now let's get on with the Python. So the goal of the Python here is basically to show you how in one shot we can get the alpha and beta for each stock in the S&P 500. We're going to use all the stocks in S&P 500 that have 5 years or so of data. The reason I want to use 5 years is because I want to match these betas to what is in Yahoo Finance. Let's say this Biogen BIIB. The only stock I found with a negative beta in the S&P 500 has negative 0.06 beta. And then Tesla, as one of the high beta stocks, has a 2.3 monthly 5-year beta. So that's why we're going to use monthly and 5 years. The other thing is we're going to use the S&P 500 index itself as our benchmark for market returns. And for the risk-free rate, for simplicity, we're going to use 4% annually. So roughly speaking, it'll be 4% divided by 12 monthly. But if you really want, you can use treasury data. It's more accurate, but CapM is not accurate to begin with. So let's just use the 4%. Okay. So first things first, like in many of my other videos, is to get a list of the S&P 500 symbols. So this is a trick where you go on a website that has a table with the S&P 500 ticker list. You do read HTML from pandas, and then it gives you a list of data frames. You take the data frame with the symbol list you want. So in our case, it was the first data frame. That's why the 0 index, and then you take the symbol column and you do 2 lists, and you get the symbol list. So just to show you guys this is how it looks like, you get SP 500 symbol list. So then now we need to use Yahoo Finance to get the data, the monthly data. So I do df equals, and I look at the autocomplete is amazing. So I do df equals yf.download. I give it the symbol list, plus I also added the SP500, the index symbol itself, GSPC, because we want that also. So this will give me the data from Yahoo Finance. So it looks like this. Basically, it's going to give me, it's going to have a multi-index with price, it's going to have adjusted close, volume, all that good stuff, and then all the tickers. So just to show you how it looks like, if you do .index, you have a multi-index. Oh, sorry, .columns. You have a multi-column index thing. So that's kind of annoying to work with. First of all, we just want adjusted close because that's adjusted for dividends and stock splits and that sort of thing. So let's just do df equals df adjusted close. Okay, so that's the first thing. Second thing is, let's take simple returns. Yes, log returns are better because with simple returns, let's say stock crashes 50%, it needs to go up 100% just to get back where it started. But with simple returns, it goes down 50%. It needs to go up 50% to go back. So log returns are better, but let's use simple returns. So all I have to do is I have to do percent change. So I do returns df equals df percent change. And I added a drop NA but I don't need to drop any here. I'll just do returns df. Okay, so I do the percent change, and let's show you how it looks like. So now I have returns df like this. So as you see, I have the returns, but one thing you notice is that the first return is missing for all of them, but for some symbols like Airbnb that were not 5 years ago traded on traded publicly, you have NaN because it's missing data. So let's have a threshold. We only want ones that have all the returns. Of course, it's always going to be missing this one. So we can do a returns.df.drop NA in place equals true. Thresh equals, this gives you like, you need at least this many non-NA values. So I do nope, that's wrong. Autocomplete is sometimes wrong. So I do returns df.shape 0, that's the number of rows, minus 1. It needs at least that many non-missing values. Access is 1. And then let's do in place is true. We did that. Okay. So how is this going to look now? So now if I go to returns df, I'm going to basically get the thing, but I'm not going to have any missing values. Okay. Oh, sorry, because I did drop access as 1, I will only have missing values for this column. So you know we can drop that too. So we can do now drop NA in place equals true, and then this will drop that column too. Okay, so now we have returns df like this. Okay, so now we shouldn't have any missing values and we're golden. Okay, so now we want to subtract the risk-free rate to get the excess returns. So like I said, for simplicity, we said the risk-free rate would be 4% annualized. So it'll be 4% divided by 12 monthly. I always say the caveat, it's not exact to divide by 12. But let's just assume this for now. Monthly equals the risk-free rate divided by 12. And then that's the monthly. So excess returns df. Let's just do, excess. Excess returns df, let's call that, equals returns df minus risk-free rate monthly. So that will be your excess returns df. So just I subtracted the 4% divided by 12 from each of these guys. Okay, but this really isn't a format that we can do our regression with. What we're really going to want, and I'll show you and make it much more clear in a second with the stats models regression, is we're really going to want to have a data frame with excess return, excess market return, and ticker. Because we're going to regress excess return, we're going to use as inputs excess market return and ticker. So if you look at it here, this is the excess market return because this caret GSPC is the market return. So we're going to need this value for each timestamp. So it's as is okay. But these things, the tickers, we're going to want to have instead of like 500 or so columns, we're going to want them as a row, and it'll have the ticker, whatever the ticker name is, and the value. And this is called basically a long format. So we're going to go from wide to long, and you can use pandas melt for that. And I'll show you the trick to do this and to keep this last thing as is. But the other ones to make just 2 columns, one with ticker and one with the value. So we can do excess, let's call it CapM df, and equals forget what the autocomplete's writing, excess returns df dot melt, and then you can do id vars, the only variable we need to keep, which was caret gspc, but remember we actually gave it a name, so we could actually use sp 500 index symbol. Okay, so what does this do? Let's just see what it does for a second. Is it what we want? So look, it keeps this column as is, that's what we want, and it gives us a ticker and a value, which is what we want. The only thing is we want to We don't need to because of what we're doing, but we probably want to keep the index thing. So you should do ignore index equals false, and you probably want to rename value to something. So I'll do value name equals, let's name it excess return. So now look, it looks a little bit what we want. The only thing is we want to name this as excess market return, and let's do a caret thing. So I'll do rename SP 500 index symbol excess market return access equals columns, and now I have excess returns excess returns df equals excess returns df, like let's call it CapM df. CapM df like this. Okay, so now we have CapM df. It's the format we want, which is excess market return, ticker, and excess return. So we're gonna predict this guy from these two variables, and I'll show you how this type of a problem can give you like all the alphas and betas at once using stats models. But let's first take a tiny digression into stats models, especially for those who don't know R. So stats models allows you to use like a formula syntax to do regression. So like, for example, if you have y tilde a plus b, that means columns a and b are your inputs, and you try to predict y from that. You also have an intercept term, but there's like another thing. If you have a times b, it means all the interactions between a and b. So you'll have it basically expands to a. You predict y from a, from b, from a times b. Those together. It's weird that they use times for the notation, but a and b together, meaning both those features together, plus the intercept. And we're not going to use it here, but you could also do subtraction. You can do like minus b minus 1. This basically means remove feature b, remove the intercept, and then you'll just be left with a plus a times b. It's weird that the times is the colon, but the times like this is like all the individual and the individual and the interaction term. Okay, so that's one thing about stats models. The other important thing with stats models, and I'll show you this cool Gemini trick, is like with stats models, when you have categorical variables, in our case ticker, it does a one-hot encoding of them, but it removes the first category, which is redundant. So if I say like, look at this cool Gemini thing, you could say show me how, give me a toy example showing how stats models handles categorical features. And look, it'll give me an example. Okay, so I'll copy and paste that. So look what it does. Oops, sorry, wrong copy and paste. So I copy and paste it, and look. Okay, so I look at the regression results. I get the the main thing is I put the formula object in smf.ols because I do from stats models formula.api as smf, and then I put the formula, the data, and I call .fit. This created a dummy data frame with sales, advertising, and the categorical feature of city. And what I wanted to show you here is city has New York and Paris only, but there's also London. But if you do alphabetical order L, M, N, O, P, you'll see that L comes before M, N, and P. So it dropped the redundant thing, because let's say for the indicators, if it's not New York and not Paris, we know it has to be London. So it automatically drops that, and that's a key point we're going to be using when we're going to do the regressions all at once. So in our specific case, we have both these things. We're going to have an interaction term. We're going to have our interaction term is going to be it's going to be ticker with ticker with excess market return. So it's going to do what I said at first with the interactions, meaning keep the individual tickers and the excess market return, but it also does this one hot encoding. So practically what that does is, let me pull up the Medium post that I had to fix a million times. Practically what this does is our regression is going to look something like this. First of all, our Y that we're going to try to predict is going to be excess return for asset 1 at time 1 through excess return for asset N at time 1, all the way up to excess return for asset 1 at time T, and then excess return for asset N at time T. And T, since we use monthly data for 5 years, is about 60. And N is like 500 assets. So that's the target we're trying to predict. But what I said about the input, and if I can make this bigger, is, okay, so we have the interaction term, plus we have the, we have to note the redundancy when it does one hot encoding. So the individual terms, first of all, there's the intercept, and the individual term, excess market return at time 1 through excess market return at time T. Let's just look at one of these vectors because that's what the notation's for. So what happens is now is you have two things. You have the individual, which is excess market return, and you have the individual for the ticker. The ticker individual one is indicator, meaning the one hot encoding of ticker 2 through ticker N. And I wrote ticker N somewhere here because it drops the first thing, ticker 1. I indexed from 1 to N as opposed to 0 to N minus 1 just to make it very clear that it dropped ticker 1. So you won't be confused. Okay. And now there's the interaction term. So the interaction term is excess market return at time 1 times indicator ticker 2 through excess market return times indicator ticker N. So that's how we get both the interaction and the one hot working together. And let's make it crystal clear what happens. Okay, so now let's say we have our coefficients, right? So our coefficients would be like this thing here, right? So if you think about it, the alpha is basically the intercept, right, for each of these guys, right? So let's say we're interested in ticker 2, right? So for ticker 2, indicator ticker 2 is going to be basically 1, and indicator ticker anything else is going to be 0, right? So for the alpha for ticker 2, if you think about it, let me take a step back because I always confuse myself. Let's think about the easiest thing, ticker 1, right? We want to find its alpha. So if ticker 1, if we're at ticker 1, all these indicators are 0. So this all goes to 0. And then you're just left with the intercept and the excess market return for ticker 1, right? And I made it a little confusing. I should have just done one row because this is like for every example. I wanted it to line up with this. But anyways, so for ticker 1, we're thinking only about ticker 1 right now, right? All these things go to 0. You only have the intercept and the excess market return at time 1. So that's easy. So the alpha is just basically the intercept, right, for ticker 1. And the beta is just the excess market return at time 1, excess market return, that coefficient, that's the beta. And then for the other ones, it's a little bit more complicated because you're going to, if you think about it, for the other ones, let's say we're doing ticker 2, all ticker 3 through N are 0. So ticker 2 basically has excess market return at time, this confused me, as excess market return times indicator ticker 2, that coefficient plus excess market return, that's going to be its beta. You're going to have to add the intercept, you're going to have to add the coefficient for excess market return to the betas, and for the alphas, it's basically you only have the indicator ticker equals 2, so you add the intercept for each one. So let me just repeat this one more time because it's really hard and I don't want to edit the video. So okay, so we want to eventually compute our alphas and betas, and remember alphas and betas look like this, these guys here. So alpha is here, beta is here, and that's what we want. And this is the market return. Okay, so the easiest one is for the redundant one. The redundant one is basically what happens is ticker 2 through n, they're all going to be 0. So the alpha is just the intercept, and the beta is the coefficient of the excess market return. That's easy. So for any other ticker, let's use ticker 2 for simplicity. What's going to happen if we want to find the alpha, everything else is 0. So we're going to have the coefficient for just indicator ticker 2 and the intercept. That's our alpha. So basically, in other words, we have to add the intercept to get the alpha, right? And for the beta, very similarly, we have the interaction term, excess market return, times indicator ticker 2. So for the beta, we're going to just have to add the coefficient for the excess market returns overall to the individual ones. And of course, we do this for all n. Let me not get too much into the details because I'm confusing everybody. But it's very hard to explain. So now to do all the 500 regressions at once, we're going to just copy and paste this boy here. I guess I don't need to paste that. I can do model equals and here I'm going to have excess returns, and then here it's going to be excess market returns. And then if it's a pandas category or a string, usually you don't have to explicitly write C, but it's better practice to say it's categorical. Ticker, I probably made a mistake. Let's see what mistake I made. Was it called tickers or something? Oh, I didn't put the data. Sorry. The data was called CapM DF, right? So now I fit this model. And what else is wrong? Excess return. Maybe I call the excess return. Let's see what we have. We have excess return and excess market return. Okay. And what did I use here? Let me just make sure I... doesn't matter. Okay, sorry about that. Okay, so let's do it the way it's here. So this is just singular. So this is the model we're fitting. Okay, so to get the parameters of the model, I showed you model.summary, but you can do model.params, and then I added a toFrame. But model.params gives you basically the coefficients, right? Okay. I don't know why this is taking forever. It should have finished. You know what? Yeah, I don't know why this is finished, taking forever. Oh, as I was gonna give up, it finished. Okay, so let's call this actually. Let's make it easier. We'll call this coef df. We're gonna do equals model.params, and you see it's like a series. It's actually a series, but with collab, you don't really see the difference between a series and like a data frame. So I'll do toFrame because I want to use a data frame. I'll do toFrame, and then I'll do coef. And then I also want to do this. I want to give the index a name. That index that name not ticker. I want to maybe I'll call it param. And then I'll do reset index in place is true, and then coef to show you guys how that looks like. So these are the coefficients. Okay, so now let's calculate the, let's start with the alphas and then we'll go to the betas. Okay, so for the alpha, remember I told you alpha 0 is very easy. It's just 0, right? It's just this one, right? For the first symbol, right? But for the other symbols, you have to basically add the intercept to these guys. But first, let's separate things out. Because for the alpha, we want the we want just the individual ticker, column. So we don't want the ones that have excess market return with them. So what we can do is we can, and let me just kind of help myself a little bit, is we can do something like this. Basically what this thing does is it looks at anything that has EXC for excess, it removes that. So then I get this alphas DF thing. Basically, because for the alphas, anything with the excess market return term, we don't want. So we get alphas DF. So now I have the intercept, but all these other ones are just these ugly things, right? So I'm going to want to parse this out and get the symbols. So to do that, we can do .param, .str, .replace. And then let's replace, like, most of these guys have like C ticker, C ticker, like this, T dot. And if we replace that with this, what do we get? We don't get anything. What did I do wrong? So as you see now, I almost have like the symbol. I just have like the thing at the end. So I can do str dot replace this with that. Okay. So I don't know what that was, but now if I look at it, I'm almost where I want. I just have the intercept term. Okay. But remember, the intercept term, we're going to need that for, so let me call this actually alphas df symbol. Okay, so now we have the symbol. Alphas df symbol, right? So now to get the alphas, remember, for the redundant symbol, first of all, to find the redundant symbol, how are we going to do that? We can do that like this. We can do alphas df dot symbol, and then that's the symbols that we have here. And then for the other one, remember we had excess returns df dot was that called excess returns df? Yeah. You know what? No, let's use the CapM df. Sorry. Df dot ticker dot unique. So let's see which ticker is missing. It's always it's the first one, but just to be like more safe, we can just make this like a to list and like a set, for example. And then so this will be all the tickers we have, and then we're gonna we're gonna basically do set difference, and we're gonna subtract the set of these symbols we got from here, and then I'll do to list. And then I'm going to get the missing one, which is going to be the A as we expected. So, okay. Oops. Okay, so that's going to be A. And then you can maybe do .pop to pop this thing out. Because sets are annoying. You can't really index them. So I can do this. So this is the, I'll call this like the redundant ticker. Okay, so this is redundant ticker. So now what do we have? We still have the alphas df as is, but I have the redundant ticker, right? So I have the symbol as we want. So what do we have? We needed to add the coefficient of the intercept to the rest of these guys, right? So I'll do dot. I'll do. You know, it might be helpful actually to do set index param in place equals true. So now I have alphas df, and now I can do loc redundant ticker to get the redundant ticker. Sorry, loc intercept. It's still called intercept for param. Intercept. Okay, so I have the intercept, right? And what do I need from that? I need the coefficient. Okay, so this is like the intercept, and this is, look at the median post, it'll be more clear. Intercept coefficient. Okay, so now I have to add this to everything except the intercept itself, right? So I'm gonna basically have to do something like this. I'm gonna have to do a good old np.where. So I'll have to do alpha's df coefficient equals alpha's df coefficient plus intercept coefficient, np.where alpha's df symbol. If it doesn't equal, its symbol is still called the intercept, right? So I'll do intercept. If it doesn't equal intercept, then you add this. Otherwise, you if it's the intercept, it's literally just the intercept coefficient, which is as is. Doesn't matter because it'll be the same thing. So it'll be like that. So I have alpha's df, and let's see how it looks like. So look, it looks okay. The only thing is we want to rename the symbol. So I'll do loc intercept symbol, and let's rename it to redundant symbol, redundant ticker. So now we can plot the ones with the top 25 alphas and betas. This is not a Plotly video, and the video is already way too long, so I'm just gonna spare you guys the burden and plot it. Of course, if there's an error, I'll help debug it, but I'm just plotting the top 20 and bottom 20. Oh, it's not sorted because we have to sort the index, that sort values coef. Yeah, oh, okay, in place is true, yeah, okay. So look, now it should be a little bit prettier. You can see the top alphas. Wow, SFCI is the best stock. I wish that was like in real life, although lately it has been. NVIDIA is obvious, because this is the last 5 years of data. Tesla, if you look at the bottom ones, you'll see some ones that are very familiar. BA is Boeing. What is WBA? What is WBA? I think I know what it is, but oh, Walgreens is that bad, really? Okay, so but Boeing is bad because we always hear bad stuff about it, so that makes sense. But Bank of America is bad, as you see. Okay, so now let's get the betas of the individual stocks. So we're gonna do a similar thing. Instead of adding the intercept, we're gonna add the excess market return coefficient, and instead of getting rid of the columns with excess market return in it, we're gonna keep only columns that have that. So basically, remember we did this guy here. We're gonna do the same thing, except now we want only ones with excess market return in the name. So I'll call this betas df, and then I will instead of not this, I'm gonna have that, and then look at betas df. Look how it looks like. It looks like this. Oh no, something went really wrong. Oh, well, you know what went wrong is because I didn't do the interaction. I need the interaction. Okay. Interaction term. Sorry, guys. So let's hope this finishes. Okay, so now we do the same thing. Might have changed a few things, I'm not sure. So now I plot it. It's still, the alphas still get the same answer because it didn't affect that. But you see Bank of America is still bad. But now, let's see if we get the betas. Let's see if this fixed it. Okay, so now you see we have everything we need. So remember, for the redundant one, it's this coefficient as is. For the non-redundant, you have to add this, but let's parse these guys out to make it a little nicer, of course, like we did last time. So do symbol equals dot replace. Wow, Google's autocomplete is very smart. I don't know if it did it right, but let's try. We have nothing to lose, right? Okay, so it did give me this index. It didn't. It kind of messed up on the on this thing. So let's actually add what it messed up on. So it wait. What did I want? I'm confusing myself because Google messed up. Just 1 second. Let's get rid of this for a second. Beta's df. Let's see what we need to do. So we're going to need to move this excess returns and the C thing, right? Excess market return. Like this. Is this better? Oh yeah, it's good. Look, the symbol is perfect. Sorry, I was looking at the index. Okay, so now we do a similar thing that we did last time with the alphas, except now we're adding something else. We're gonna do like we're gonna get the instead of intercept coefficient, I should say excess market return coefficient. And then I'm going to have betas dot log, betas df dot log excess market return dot coefficient. So we get this thing, excess market return coefficient. And then, oh look, it's smart enough to know if it's not excess market return, then why is it subtracting? It needs to add. Otherwise, that's good. So let's hope Google didn't make a mistake. And now we can plot the top 25 bottom and top stocks. I'm going to just copy and paste from my Medium post. Let's see if this makes sense. Because this we can actually judge if we did it right, more or less. We're not going to ever get exact. Oh, sorry. I want to plot this thing. Okay. Oh, it's ugly. Because x, let's not call it coefficient. Let's call it symbol. Oh, sorry. Y symbol. Oh, yeah. Let's redo this for a second. I thought we worked so hard to change it. Okay, so like, we didn't order it, of course. And we kept excess market return. We kept the name. Remember here, we also renamed it. So let's do the renaming thing for a second and sorting. So so we're going to do something like this. We're going to do betas df dot log excess market return symbol equals redundant ticker, and then I'm going to do betas df that sort values conf in place is true. And now when we plot it, it's going to look a lot nicer. So look at the these are the top beta stocks. Look at Tesla's way up there. Yeah, it says beta's 2.328 something, and let's see what it says. Yahoo Finance beta is 2.3. That's good enough for me because we don't know exactly the differences and how they calculate it. But let's do the most obvious one, the worst one. BIIB is a negative beta, which is negative 0.078. Oh, I guess this changed from yesterday. So I do BIIB. And the beta is negative 0.06. Interestingly, yesterday in the regression, I got negative 0.06 something. So I guess it changed overnight. But maybe they get rid of the last month. You know what? Let's say I'll leave it as an exercise to try to match them exactly. Okay, so the last thing I wanted to talk about, and I guess we've gone way over time, is to do the security market line, how to draw that. So basically, this is just a line of, you go all your betas, and it goes through the market return. So basically, it's just a line through the market return. So like maybe sixth grade math or something, but it's sixth grade math is harder than you think. So basically, I'll just explain what I did here. I have number of points is 300. Betas is np dot line space or lin space. It means I'm going from 0 to 2 for these number of points, and those are our betas for my x-axis. For my y-axis, excess market return. Expected excess market return, I'm just taking for simplicity the mean of the individual excess market returns. That's why I have SP500 index symbol, the mean of that. And then I multiply by 12 to annualize because this is monthly. And then the returns, SML returns, is the risk-free rate plus betas times the expected excess market return. And as you see, it kind of goes from like, you'll see it goes from 0 to the risk-free rate all the way in the middle. It's 1 and the market return, and then it goes forever. But this is boring. So anyways, hope you learned something. Like and subscribe. Join. This video was a bit hard for me. It took me a while. But hopefully some people enjoyed it. Thank you.